Okay, so for this one here, we're looking at beginnings of two-dimensional motion. So here you can see that we have a couple of motions in a city block, and you can see that one of them is 9 blocks east, and then they turn and go 5 blocks north. So without drawing anything on here, I'm going to draw on here myself, but you don't have to draw anything yet in your notes. But remember, displacement specifically, this is talking about distance right now, right? So displacement is the starting point to the end point, and that's it, right? So for the displacement for this, that's going to be this diagonal here, right? Which, if you look closely here, I'm starting to form a right triangle, right? Which means really what I'm looking at is this a little bit thicker here, but is a right triangle using Pythagorean theorem, and that is going to be what's called the resultant to this situation. That's going to be how we find the third side of our right triangle. So here is Pythagorean theorem. So, everybody thinks of it as a squared plus b squared equals c squared, and sure, that is correct. But this is typically how we have it. So go ahead and draw this picture, but be sure to include the variables on the triangle here. A is kind of cut off, and that it's a right triangle. You want to make sure that it is clearly a right triangle. And then C, of course, is that hypotenuse here. Make sure I didn't skip one. I thought I might have double tapped that. So here we have a question there. For a second, it showed all the answers, but so looking here, we got to walk 14 blocks in total, 9 blocks east, 5 blocks north. So we want to actually go ahead and use Pythagorean theorem to figure out what that is. Let me pull up my calculator here to show you. Okay, so of course, square root of 9 squared plus the 5 squared as well, and we get 10.29. That 9 is going to round that 2 up, and notice everything's in tenths, so that's where we want to round. And so 10.3 has to be our answer, because that 9 will bump the 2 up to a 3. So here we have a helicopter flying exactly that path, and it shows the calculation that we got to. So there's our straight line using Pythagorean theorem. Now, a couple things about Pythagorean theorem. So remember that when we draw it out like that, we're really looking at mostly just the vector's magnitude, right? We haven't really delved into direction, but direction matters too. And hopefully the resultant arrow that we got at the end there should be pointing to the same endpoint that the other vectors, the other individual vectors end at. And those other vectors are called components, and we'll talk about the definition of that here in a moment. So some more about Pythagorean theorem here. But really it's just talking about how to add and subtract vectors, and including other methods that we'll see here in a little bit. Now, one thing we need to keep in mind when we start to talk about two-dimensional motion is that perpendicular motions are independent of each other. So if we are looking at a horizontal and a vertical motion, those two motions do not affect each other. Same as if we are looking at walking in the city. The eastern motion has nothing to do with the northern motion and vice versa, right? They're two independent pieces, but we can look at the displacement between them instead, and that gets us something else, but it's the two are independent of each other entirely. And the same goes for projectile motion when we look at that here in a minute, or later, that those also will be independent of each other. And so here's an example of some perpendicular motions as well, starting to kind of get into projectiles here. So you have two balls here. One is red and one is blue. Pardon me. The red one you can see is dropped, and the blue one is rolled off of a table or a cliff or whatever the case may be. Both of these balls have a green arrow pointing down, and the green arrow, notice as it falls, is growing. It's getting bigger because it is accelerating downward using gravity, just like our free fall situations, right? But the blue one, since it is rolled off of the table as well, has a horizontal velocity, and that horizontal velocity is constant. So notice all of the black arrows pointing to the right are the same length. So they are remaining constant. Again, those two motions, once again, just like as before, they are independent of each other. Horizontal direction does not affect vertical and vice versa. Just a recap to remember displacement. Displacement, remember, is the distance between the endpoints, the starting and end, not the individual pieces of the motion. So, we already defined this, so we don't need to jot this definition down, but remember that vectors have both magnitude and direction, and just because we're looking at them in 2 dimensions now, that doesn't change. We still have both, but in this case now, instead of the direction being indicated by a sign, like a plus or a minus, the direction is going to be indicated by an arrow pointing in a certain direction, usually given by an angle in degrees, and then usually some kind of description of that angle. Then using the cardinal directions, north, south, east, and west, to just help describe it if it is on a flat surface. If it's in the air, then it's just however many degrees above the ground. So, for example, here they have this person that walked, and they have, or now the helicopter, sorry. The helicopter is flying with a magnitude of 10.3 blocks and at an angle of 29.1 degrees north of east. So the way you describe that with the north of east is that you would go, and so the way I like to think of it is that to get from that bottom x vector to my resultant vector, to my actual displacement, I would go north of east to get to it. And that's where that angle is. Now we could do these graphically as well. If we come up with some scale to go with it, we can use a ruler and a protractor to figure out the magnitude and direction respectively. Now, some notes here. They talk about it in this, but I'm going to detail it a little bit more. So whenever you talk about vectors and scalars, so in print, so really in text and print, so like when it's printed on something like this, or in a textbook, or on a worksheet, things like that, vectors are bolded. Scalars are in italics. So they have some examples here. Vector F is bolded, and then F, when it's not a vector, is in italics, and theta, angle, is just a direction. Also, goodness, I just keep yawning, I'm sorry. Theta is also in italics. Now, we can't write in bold, we can't write in italics really, and it be truly obvious that that's what we're doing. So in handwriting, helps if I can spell. Vectors have arrows on top. Scalars don't. So for example, we usually do like a little arrow. I like to do like a half arrow because it makes it a little bit neater for me, but whatever you prefer. But that's how you indicate between scalars and vectors whether you're going to have just a magnitude or a magnitude and a direction. So a couple things we want to write down here. I know it's not a writable slide, so give me a second I'm going to pull up a screenshot here so I can write on it. So this is the graphical method we're going to use in this class, but there are other methods to do this graphically, but we're only going to really talk about this one. This is the head to tail method. I didn't write all that down. Just that the head to tail method is the graphical way to add vectors. And then, so the components of that, so the tail of the vector is the starting point of the vector, and the head of a vector is the final pointed end of the arrow. So there's some easy, quick definitions there for those things. So the way this is going to work, I'm just going to describe it in the next slide here. There's multiple slides broken down, but we're going to just look at it in this one. They do define resultant vector again here, but we're going to define it later because it's better later on. But so you start out by drawing the first vector. You can see in picture A there, they do draw a 9-unit vector, and then they go from there. From the head of the first vector, you start to draw the tail of the second one. So head to tail, that's why it's called that, right? We don't get super creative with our naming systems in physics. But then you would draw that other vector after that, which in our case is 5 units north. Always making sure that you draw the individual vectors in the direction they're supposed to go in, right? So one was east, so that's directly to the right. One was north, that's directly up. And then you connect the original vector's tail to the final vector's head, and that is your resultant vector. In this case, you would measure that out, multiply it by some scale. So they measured out to be 10.3 units. If we had a scale after that, we would have to multiply by it, but really with 9 and 5 being the numbers, you don't have to really worry about that too much. But then use a protractor from there at the origin to figure out what the angle is of vector D in this case, or we usually use R a lot of times to represent the resultant vector. So they do break it down. So step 1, draw the first arrow. Step 2, draw the second arrow. From the beginning of the first, or the end of the first one is where you start the second one. And then connect them and multiply by any scales that were necessary. Then, of course, they go ahead and define magnitude and direction again, but we're not worried about those because we already know what those mean. Now, of course, in this case, the magnitude is the length, the direction is the angle with the protractor. So here's another example. Now, you don't always have to just have only 2 vectors to add together. If you're adding vectors graphically, you can add as many vectors as you have. And the nice thing here is that it doesn't matter the order. Just like adding numbers, it follows the commutative property, so you can add them in any order. So we have these vectors here that are 3 vectors, A, B, and C. Vector A is 25 meters at 45 degrees. Vector B is 23 meters at 15 degrees. And vector C is 32 meters, really at a negative 68 degrees. But it's 68 degrees south of east instead of north of east, like the other 2 are. And again, you can use the head to tail method as before. Combine them together in the same way. So A to B and then B to C. Draw them all out as they were before, head to tail, and then your resultant is still the beginning vector's tail to the ending vector's head, and that gives you your resultant. And once again, it doesn't matter what order you do that in. So here's an example of them adding them A plus B plus C, but you can also add them C plus A plus B, and you still get the same number, 50.8 meters and 5.47 degrees. In this case, it should be a negative, by the way. I don't like that they don't label that, but if you do describe it as being south of, where is it? Here it is. Now they put 7, so I don't know, but it should be south of east. They rounded everything for some reason on that slide. I don't really know where those numbers came from. Vector subtraction just means that you're going to add the negative vector to it instead of that, and in this case that just changes the direction of it, right? So instead of our arrow pointing up and to the right, it's now pointing down to the left. And you can break that down just like I mentioned, adding the negative version, and you can do that graphically as well. So here you have vectors a and b. We're going to add the negative b, or subtract b away from a. So that just means that b goes the other direction, negative b, down there at 68 degrees south of east instead of 112 degrees north of east. And then you add those together like you would normally. So here we have our a plus negative b, or a minus b, to get the resultant. That was 23 meters at negative 7.5 degrees, or 7.5 degrees south of east. And if you were just to add the two vectors normally, instead of subtracting them, here's what you would get. Just for reference, that they are completely different numbers. We did not get the same thing out. 52.9 meters at 90.1 degrees. So there we go on that. Now when you multiply a scalar, like there's some number by a vector, you're just really making the vector longer by whatever you're multiplying by. If you're multiplying a scalar quantity that is actually like a measurement, like mass, or don't know really the case, you would just use speed, but mass is a prime example, or temperature, things like that in an equation, and you're multiplying that by something that is a vector, so velocity, acceleration, things like that, then you're going to get another vector back out. It just will change what the quantity is referencing instead of being just a multiple of the original. It'll change what quantity we're talking about now instead of just a larger version of the former quantity. So here we do have one bit of a definition. It's still not great for components, but it's better than it was before. So the components of a vector would be like the x and y components, or the north, south, east, west components. So that just means like the pieces to the vector that are specifically in the x and y directions, or if you want to go north, south, east, west directions, that's fine. But typically we go x and y directions. So there's an x component and a y component for every vector. Some of them might be 0, but they still will have 1. We're not going to define this because it's just talking about doing this mathematically. And we're going to look at this basically at first, and then we'll jump into it next time with it really adding two vectors graphically. So to start, I do want to draw this picture, but not yet. I actually want to add some more detail to it. So on this one here, we just have this vector A, AY and AX are the components of that vector. We need to figure out how to find those. So here we have the fact that we can't just add them together, right? So if we have a right triangle with sides 3, 4, and 5, that does form a right triangle. But 3 plus 4 does not equal 5, right? 3 plus 4 is 7. So we can't just add them up like we would normally with numbers. So there's some other way we have to do that, because we know they're forming a right triangle. We know that the numbers aren't going to add up like they would normally anyway. So we have to use something else, and that's where trig is going to come into play. And so real quick, I'm going to give you a crash course in trigonometry, because some of my students have not had geometry yet, or are in it right now, and I want to make sure that you know what you're doing with that. So here is a couple things listed. We do want to write those down, what AX and AY are specifically for this problem. But here's our crash course. So we have 3 basic trig functions that we're going to look at in this class. There are more, but we're only going to focus on 3. And they go along with a phrase called so, ka, toa. So in SOHCAHTOA, if you break it apart 3 letters at a time, so is sign. Oh, hold on, I'm going to color coordinate this like I did before in my notes. So this is sign, but we abbreviate it to be SIN. So sine of our angle theta is equal to the O and H stand for opposite over hypotenuse. I'll draw a picture of what that's referencing here in a moment. Cosine, we abbreviate to be COS over angle theta. So the A and H go along with the adjacent side of the triangle, and again the hypotenuse. Then we have tangent. That's our third one. So tangent, we abbreviate just as tan of our angle again. And really, I like to put these in parentheses, but it doesn't really matter that much normally. If there's a lot of work going on inside, you do want to definitely do that. But anyway, the O and A again are still referencing the same thing. O is opposite. A is adjacent. So what is all this talking about? Well, if we have a right triangle with an angle theta, the side across from that is the opposite. The side that forms the angle theta with the hypotenuse is the adjacent side. Now, if you really want to get fun with it, SOHCAHTOA, and there's an abbreviation that goes with it. It's not super appropriate for school, so I'm probably not going to say it actually. But, well, whatever. It's some old hippie caught another hippie tripping on acid. Helps to remember the phrase if you can't remember SOHCAHTOA. Well, maybe that'll help you out a little bit. Just like, please excuse my dear Aunt Sally, right? For PEMDAS, just a little less appropriate. But these are our 3 main trig functions, and we're going to use them. You can see here, AX is equal to A times cosine theta. That goes along with that. For the most part, cosine always goes along with X, and Y also goes along with sine. So AY is equal to A times sine of theta. So moving on to that picture we saw earlier, here we have this again. Now, I don't quite want to draw it just yet because there's one more thing we wanted to discuss. So now, with these, we know how to find our components of a vector given the angle and the magnitude of the original vector. So, for example, here, back to that original example we had, where we have a vector of 10.3 blocks, angle of 29.1 degrees. If we work backwards than what we had before, and we do A, so 10.3 times cosine of theta, 29.1, we get about 9. It's actually like 8.999, so they rounded to 9.0. And then for the 10.3 times sine of our theta, 29.1 degrees, that is going to be about 5.11 or 5.0001, something like that. But do be cautious. You want to make sure when you're doing trig things with sine, cosine, and tangent that you make sure your calculator is in the right mode. So on Desmos, for example, you can see here there's radians and degrees at the bottom. If I have that in radians and I do this calculations, it's going to give me very wrong numbers. Likely something very low number-wise. So just be careful, or if you get something very, very small, double check the mode of your calculator because it likely is not in the right mode unless it's just referencing something very, very small, which is possible, but less likely. So these are the other 2 things I want to add on here. We're going to go ahead and write those on our notes, but I'm going to draw that picture here in a minute to combine it together. Now, there's a typo here. They put the exponents on, I didn't mean to make that a highlighter, but on the subscripts for some reason. So it really should be a is equal to the square root of ax squared plus ay squared. But really, that's just Pythagorean theorem, right? We already kind of wrote that down earlier. And then the other one is the inverse tangent. So we didn't talk about that, but those three trig functions, sine, cosine, and tangent, also have inverse functions that basically are like the subtraction to the trig functions addition, where you would use those to find the angle given the sides that go along with whichever trig function you're using, sine, cosine, or tangent. For our case, for looking at the resultant vector, that's going to be inverse tangent specifically. So this is the picture we want to draw, but I am going to add on to it. It's now lacking the other parts, the component pieces. So ax, remember, is equal to a cosine theta, and ay is equal to a sine theta. So add those things in there. And now we have everything we need in that picture. So make sure you draw this triangle here for your reference. Remember too, if I go too fast, feel free to pause at any moment. I think that's where we're going to stop, but I want to make sure. Okay, so we're going to keep going. Can't remember where we're going to stop out, so I might go too far. We'll see. So equations here to find the components. This is basically just word explaining everything that we just talked about and drew in that picture. So if you're going from the magnitude of the vector and the angle to the components, use that ax equal to a times cosine theta, ay is equal to a times sine of theta. If you're going from the components to the magnitude and direction of the vector, you're going to use the Pythagorean theorem and inverse tangent. And that's pretty much all there is to it. Now, if we have two vectors that don't make a right triangle, we're going to have to use all of these things at once. And that's where we're going to stop. So this picture here, we're going to solve this resultant vector here with some actual numbers added onto it. But this is where we're going to end for now.